So we are talking about mass spectrometry. Last time we went through some problems on determining molecular formula using isotopic abundances. Okay, so we went through those, and then we just got to the point of introducing some fragmentation mechanisms. So we're going to do a little bit more of that, and then we're going to start just working through kind of different functional groups and see how the predominant cleavage patterns are. Okay, so, all right. So the next thing we want to look at is the fragment ions. Okay, so we've talked about the molecular ion mostly so far. So we want to talk about fragment ions, and we're going to look at a number of different cleavage mechanisms. All right, so we'll start with the main ones, and then we'll see a few other ones as we go through. There's lots of different ones, but we're not going to look at every possibility. Okay, so the first thing we need to know before we talk about fragmentations is for a given molecule, where's the likely place, and we talked about this a little bit already, where's the likely place that the molecule is going to ionize? Because if we're going to draw a mechanism, we have to know where the charge or the radical are. Okay, so most commonly, so the ionization preference, and I think this just has to do with the ionization potential of the different electrons in the molecule, is usually going to be non-bonding electrons is going to be more than pi electrons and more than sigma electrons. Okay, so the first one we're going to look at here is called a sigma cleavage. So this is from a sigma bond, and because that's the least likely to be ionized, this is going to be most common when there aren't other functional groups, for alkanes and things like this. And we kind of talked about this a little bit. In this case, if we have just some alkane like this with a sigma bond, we ionize it, we shoot it with electrons, we form our molecular ion, right? So this would be our molecular ion, and it's an odd electron ion. And essentially, we've just weakened that bond, and so this can cleave in two different ways. The left R group could be the radical, and the R prime could be the cation, right? And notice this cation that's generated is an even electron ion. Or it could fragment in the other direction. So the R is the plus, and the R prime is the radical. Okay, and remember, when we run the spectrum, all we will observe is the cations. We don't observe the radicals. They just get pumped out into the vacuum pump. All right, and we often see the loss of the larger radical. Unless, well, what we usually see is the most stable cation is formed. But if we have two cations of equal stability, then we see the loss of the larger radical. If equal stability, loss of larger radical.
Why a little larger radical?
I don't know why, but that's just the empirical observation.
It goes out from the instrument, or?
Yeah, the radicals, they just, because remember in EI, we're doing this under high vacuum. We have a vacuum pump that's pumping it out. So anything that we don't observe, there can be other things formed. We could have anions that are formed in the process or neutral species. Any of those will just be pumped out.
With the neutral species?
Yeah, and only the cations get accelerated down this flight tube and down the...
And the smaller ones, probably.
Well, all of the cations will be accelerated and will be...
If they have equal stability.
Well, these will all be observed. I'm just saying if they're equal stability and we see more of the loss of the larger radical, but remember, these are all just competitive mechanisms taking place at the same time. Right? Like we'll look at some more spectra, but like we saw before when we had an alkane, we see, a bunch of different peaks, but we didn't see a lot at high mass. So we didn't see, if we had a decane, we didn't see a lot of loss of methyl group. We saw more cleavages in the middle and losses of more abundant ones where we lost a bigger radical. Right? But it's all competitive, and so we'll see a whole bunch of different ions, right? We don't just see a single one. Right? Okay. All right. So the next one is called a homolytic cleavage. And so based upon that name, homolytic, this is, homolytic is when we cleave a bond evenly. I guess we can draw these down here. So if we had something like this, so if we had a homolytic bond cleavage, means we're going to cleave the bond with an equitable or even splitting of the electrons, right? So this would give us two radicals. If we have a heterolytic cleavage, then we have an unequal splitting of the electrons, and we would end up with one of these with both electrons and the other one with none of the electrons. Okay? So homolytic cleavage is usually going to be a radical induced mechanism. And this one is oftentimes referred to as an alpha cleavage. All right. So typically this is going to happen when we have non-bonding electrons or pi electrons. Okay, so let's look at a situation here. So I'm just going to put a Y group here. It's going to have non-bonding electrons on it. It could be oxygen, nitrogen, sulfur, different groups like this. Okay, so we're going to shoot it with electrons. We talked about if we have these possibilities, then the non-bonding electron is going to be where the ionization takes place rather than sigma bonds, like we saw up above. So we get this Y with a plus and a radical like this. So this is the molecular ion. And notice because it has an unpaired electron, this is our odd electron ion. Okay, so the radical-induced mechanism is going to take this radical. Remember, when we draw radical mechanisms, then we use a single-sided arrow showing the movement of a single electron. So that electron is going to go down here, and it's going to combine with one of the electrons from this other sigma bond. And that bond is going to homolytically cleave. All right, so this bond right here, one electron is going to go to the left, one electron is going to go to the right. Okay? And what we get out of that is that we have this R to Y. We're going to have a double bond over here now. Still has a plus charge on it. And we're going to lose this R prime radical. So I think the idea is that this would be the alpha carbon, and we're cleaving just on the other side of the alpha position. Right, so that's why it's called an alpha cleavage. Okay, and notice that like before, this is an even electron ion, and we're losing this neutral radical. All right, so we could, well, we'll show other examples later, but this could also be done if we had, say, a pi bond. When we ionize it, the way we draw this is that we can draw, so in this pi bond, there were 2 electrons over there, and now we've lost one of them. So we have a plus. We can draw them together, or usually we draw them a plus on one side and the radical on the other, but we could do it either way. Yeah. Okay, but once we have this radical, we can do this alpha cleavage. So this radical goes here, combines with one from over here, and we do the homolytic cleavage of that bond. So what we would get is this plus this. And so notice what we're generating here is this allylic cation. Right? So that cation is stabilized by resonance. And this is also the even electron ion. And if it's, if it's just some double bond in a chain, it could cleave the other direction as well. All right, so we'll look at more examples as we go, but let's look at this other one, the heterolytic cleavage. This is going to be a cation-induced mechanism. So from this radical cation, instead of showing a mechanism that uses the radical, we're going to have a mechanism that uses the cation. Okay, so these are commonly like this. So we could have this same kind of group that we did before, oxygen or nitrogen or something like that. We're going to ionize it. Electrons. We're going to generate our molecular ion. I'm going to draw the plus on this side now. R prime. And in this case, what it does is it cleaves the bond that's directly attached to the heteroatom. And it's going to move a pair of electrons, so it's going to be a double-sided arrow, and those electrons are going to go towards the plus. And so if that takes place, then we end up with Y. We have a radical here. We got that pair of electrons. So this is a neutral radical plus. The plus is going to be on the alkyl side this time. Okay, so the cation's not going with that heteroatom. So here's our even electron ion over here. It's our odd electron ion. All right. All right, so the next one is going to be some rearrangements, but I think since it's almost time. Let's just pick those up next time. Okay? And then once we finish those rearrangements, then we'll look at a few kind of general rules, and then we'll start just kind of going through different functional groups and looking at how those functional groups cleave. And then we can get to unknowns. This is where we finished up last time. And so we looked at these three cleavage mechanisms, which kind of relied on this point up here, because if we're going to draw a mechanism on how the molecule falls apart, we need to know where the reactive position is, which is the ionization point. Okay, so if we have a molecule that has basically only sigma bonds, and really only a hydrocarbon, then what we see is this sigma cleavage. And this is just ionization of a sigma bond somewhere in the molecule. And once this bond is weakened, then it can split. And so we get a radical, which we don't see in the spectrum, and we get a cation. Okay? And it can go either way, split either way. Though in general, if these cations are of different stability, we see more of the more stable one. If they're of equal stability, we see more of the loss of the larger alkyl group, the larger radical. The next one was this homolytic cleavage, also called an alpha cleavage. And this oftentimes happens when we have non-bonding electrons like oxygen or nitrogen, or if we have pi bonds. And so because it's homolytic, this is a radical mechanism. And so it's the radical which triggers this thing. And so the radical goes down, combines with one electron from the adjacent bond, so on the other side of this alpha position, and it cleaves that bond to form this alkene. So then we lose this neutral radical over here, and we get this even electron ion as the cation that we can observe. The same thing can happen if we have an alkene. If this gets ionized, we can draw the plus on one side and the radical on the other, or we could draw it the other way around, so it can cleave to either side. We do the same kind of electron pushing, and we get this allylic cation and the loss of this radical. The last one we did was a heterolytic cleavage. So this is the cation which is inducing this one. So again, we ionize on the non-bonding electron, and it's the bond adjacent to the heteroatom that gets cleaved, and it's a pair of electrons that goes towards that non-bonding, or toward the heteroatom, to give even electron ion over here, and then we lose the heteroatom as the neutral radical. Okay? So those are the ones we've seen so far. So the last one we're going to really look at, we're going to see a couple of other rearrangements as we just go through the problems, but we have a couple of different rearrangements to look at here. Okay, so in general, these reactions are something like this. I'm going to just put in a Y group here that has non-bonding electrons, and I'm going to draw it like this. So this is the alpha position, beta, gamma. Okay, so like before, when we ionize this, it's going to ionize on the non-bonding electrons. To form this radical cation. Excuse me. So this, right, is an odd electron ion. And we know that if there's odd number of nitrogens, it'll be odd mass. Even number of nitrogens, it'll be an even mass. Okay, so if we have a hydrogen that is on this gamma position, then that hydrogen atom can be transferred to the heteroatom. Okay, so we can draw it like this. We take this electron and it combines with one of these electrons over here, and then this bond cleaves. So this step doesn't involve any change in mass, but it's just an intramolecular hydrogen atom transfer. So now we have a radical over here. All right, so now this radical can essentially do an alpha cleavage. Okay, so which means that this is going to be pushed down here. This other bond is going to split with one electron going to combine with the first one, and this electron can go over here. So when it does that, we end up with a radical like this, and we've lost this alkene as a neutral fragment. Okay, so notice, different from the other mechanisms that we've seen, we're starting with this odd electron ion over here, and what about this fragment ion that we just generated? Is it an even electron ion or an odd electron ion?
Odd.
Odd, right? Because it has that radical on there as well. Okay? And so in this case, if we have an even number of nitrogens, right, it's going to be an even mass. What about this odd electron ion fragment? Should it be an even mass or an odd mass? An even, right? Because it's also has an even number of nitrogens. It's also an odd electron ion, just like a molecular ion, right? So if this has an even number of nitrogens, then it would have an even mass. Okay, so this is a way we only generate an odd electron ion as a fragment ion if a rearrangement took place. Okay, and notice the difference. So usually we get an odd mass. We start out with an even mass, but it's because this hydrogen was transferred over to the side where we end up with the cation, right? So it's one mass unit higher than it would be otherwise. Okay? So one version of this would be with a ketone or some type of carbonyl group here. Maybe we have an R group off of here. So when we ionize this, it does just like we did up above. So one of the non-bonding pairs of electrons on the carbonyl would get ionized. Okay, one of the hydrogens from this gamma position can be transferred to the oxygen. Okay, sometimes draw these two steps all in one. You can, but okay, so we have this species now, right? We've just transferred the oxygen, and now we can essentially do, this was here, this was the alpha cleavage. We can do an alpha cleavage from here. We get this odd electron ion. Okay, so this is the McLafferty rearrangement. If I even spell it right. Okay. So what we'll see, so this is going to be an even mass over here. So if in the spectrum we see a molecular ion is even mass and we see another, predominant fragment that has an even mass as well, we're going to look for one of these rearrangements. Okay, and that's going to give us some structural information. Okay. You can also have these types of rearrangements with other types of pi bonds. So let's say we have something like this. And this gets ionized in the benzene ring. Okay, it's going to be one of those double bonds. Of course, it's all in resonance, but we can choose how we draw it. I'm going to draw a radical here and a cation here. Right, so we've just essentially lost one electron within the benzene ring. And I'm going to localize it here to draw our mechanism. Okay, so the hydrogen, so there is already one hydrogen here, right? Another hydrogen can be transferred to the benzene ring. And I guess I'll just put this down in there. So now we have two hydrogens over here, plus here, and a radical over here now, which can then do the alpha cleavage. Okay, so again, we end up with this odd electron ion. Okay. So they're both essentially the same type of mechanism. All right. Okay, so before we look at some actual spectra, let's just go through some kind of general arrangements. That's like this bottom one. Right, except in this case, we had a carbon here, but in the example we just did, it's just an oxygen here. Right, chlorine out there. Okay. So I don't know if these are really rules, but some general trends. Okay, so the relative height of the molecular ion is greatest for straight chain. I guess if it's an alkane, for a straight chain alkane, right? And it decreases with increasing chain length. It would also decrease for, here it is, for branched alkanes, because we have a more easily formed ion, so the molecular ion doesn't stick around as much. Okay, cleavage is favored at alkyl substituted carbons, right? And so this is basically following the stability of the carbocations. So at a tertiary position should be more stable than secondary, more than primary, more than methyl. Okay? Though we are in a very high energy situation, right? So we do end up seeing ions and cations that we wouldn't normally see in a, just a normal reaction mechanism, right? That you're running it in the hood or something. Okay, double bonds, rings, and aromatic rings can stabilize the molecular ion, right? So it's either going to be substitution or resonance can help stabilize a carbocation. If we have cyclic alkenes, they favor an allylic cleavage. This is what we showed before, which gives us an allylic cation. So if we had a cyclic alkene like this, then this would ionize. We can draw it with a radical on one side and a plus on the other side. And, oh, why did I draw in the, I don't want those other double bonds, though.
Habit.
Huh?
Habit.
I know, it
Yeah.
started into a benzene there. All right, and then this can essentially do this alpha cleavage here. Okay, so even if we do this, oh yeah, we have lost, so we've gone to here. Lost this and a plus over here. Is that right? No, I didn't break. Oh, I didn't break that other bond yet. Sorry. This isn't there. This is like this. All right, so we end up with this allylic cation, right? So that plus can be delocalized. Of course, when we've cleaved that bond to get to here, there's been no change in mass yet, right? We haven't lost anything. But so this can go ahead and do this alpha cleavage here, which would give us this double bond here, with a plus, and a radical. Okay, and this is essentially what this next one says, saturated rings, okay, this is different, lose alkyl side chains off of rings. Cyclohexenes do essentially what this is, and this is essentially what's called a retro Diels-Alder. So remember the Diels-Alder reaction. Alder is the reaction of a diene with an alkene. And it's this kind of 2+4 addition. The electrons go around in a circle like this, and we end up with a cyclohexene. Okay, so in the reaction that I drew up above, we started with a cyclohexene, and we ended up essentially breaking the bond here, so we essentially did a reverse of this Diels-Alder reaction. Okay, so this is the retro Diels-Alder. Okay, just a couple more here for alkyl substituted benzenes. The cleavage, this is in blue, is usually, I guess, well, beta. I don't know if that's the right terminology there or not. So if we had, kind of like we did before when we did this rearrangement, if we ionize this, we'd knock out one electron in the benzene ring, and we can draw it however we want, where we have a radical and a plus. Right, so then this can do an alpha cleavage like this. So we end up with this plus R Okay, so usually this kind of species is said to kind of rearrange here. Okay, so first off, we can just show a resonance. This could move down here, essentially reforming the benzene ring. Right, so this is a benzylic radical. No, cation, right. Or benzylic cation, right, which is going to be pretty stable anyway, but I guess what they always show is that this can actually rearrange further. This bond can expand. Let's see, so these two actually, this is just resonance here. And then this can expand. If that bond jumps up there like that, it goes to a 7-membered ring. And we have 2 H's up here, so that's the CH2 group. Plus is on this double bond like this. And then this goes through a further rearrangement, a 1,2 hydride shift essentially here. And we end up with cation like this. Okay, so this one, you know what this is called? 7-membered ring with...
Cycloheptene.
Well, it has kind of a common name. It's called a tropylium ion.
Guy would have never known.
Very systematic.
Yeah.
Oops. So why is this a special ion that gets a special name like that?
My guess is that that's still aromatic.
It is aromatic, right? Because there's 7 carbons, but there's 6 pi electrons, just like in benzene. And there's p orbital on all of the carbons. So this is aromatic. All right, so this tropylium ion, just like the benzylic ion over here, M over Z equals 91. Okay, M over Z equals 91. So for aromatics, sometimes we'll see, we talked about before, I guess you remembered the 77, right?
Yep.
So 77 is a cation like this. It's just a phenylcation. But the benzylic cleavage gives this tropylium ion, which has a mass of 91. And notice they're just, 14 mass units apart.
Shocker.
All right, so let's see here. This, I think, wasn't quite right when I was looking through my notes. Let's just say the sigma bond next to a heteroatom, those are frequently cleaved. So this was the heterolytic cleavage, like this, which gives this radical plus this cation. And for heteroatoms, it seems like what I notice is this is more prominent for oxygen than for nitrogen. Nitrogen tends to do more of the alpha cleavage because it ends up with a positive charge on the nitrogen. And nitrogen's better at holding the plus charge. Okay, so sometimes we can also see cleavages where we lose some small stable neutral. This often requires some type of rearrangement. So we can lose carbon monoxide, alkenes. We've seen loss of those in those McLafferty type rearrangements. You can sometimes lose water from an alcohol sometimes. Ammonia or an alcohol, sometimes we see losses of those. But each of these, since we're essentially losing molecules, is that we will generate a odd electron ion because it's a rearrangement. All right? Okay, so let's look at some spectra. Okay, so here's just decane. And like we saw, we looked at dodecane before. Okay, so this is going to be C10H22. Molecular weight is 142. Okay, so we do see some molecular ion here at 142. And then what we would notice is that we see, 85, 71, 57, 43. I guess this is probably 29. So we're seeing these ions 14 mass units apart. Okay, and we can draw these. These are just going to be sigma cleavages because that's all we have in this molecule, and we can just kind of draw where the cleavage would be if it was cleaved here and the charge stayed on that side, then that would give us 29, right? And we can do the same thing as we go up, right? 43. 57, 71, 85, right, like that. And we see some other small ions in here, and I was trying to read about that yesterday, and in this McLafferty book, he says that because there's so much energy in these, partly because you need more energy to ionize these, so the molecular ion that gets formed has more energy in it, that you get a bunch of kind of random rearrangements. And I couldn't find out in there, some of them, what they were, pushing electrons enough to pick out all of these, small things that are in there. All right. So I think, like I said before, this is kind of like IR. We're not going to assign every peak, but we'd like to assign some of the major peaks, some like the base peak and some of the higher mass peaks. Okay? All right, so this is 4-methylnonane. So 4-methylnonane has the same mass, so 142. We can still see that here. And what we should expect here is cleavage around the branch point. Okay, so if it cleaves here, and the charge goes with the more substituted side, then this would give 99. So that's actually this one here. So I was trying to figure out what that 98 was, and it's a loss of another hydrogen. It has to have some kind of rearrangement to get there, but I didn't find an actual pushing mechanism to to show how that's formed. It cleaves here, kind of the same thing. 71, that's this one right here. So there's also that big 70. And then we see some other ones as it goes down, 57, 43, like this. And I didn't really figure these out, but once you can, oftentimes, if you generate an ion, let's just see how this works. So if we generated this ion here, this would be 99. Okay, but then you can kind of get elimination reactions, essentially. So this bond can cleave and go like this. And if it does that, it ends up with this neutral alkene plus a new carbocation like this. And I think that this is actually 57. Or if we do it the other way around, maybe if we go from, let's see here, 71 plus like this. So this would be m over z equals 71. Well, that's not going to really do. I'm not sure about the 40. So 43 should be a propyl cation. But if this cleaves in the same way, then that would give 29. And we see a small amount of that, but not too much. So, I guess it could be just cleavage like this. I don't know why it would necessarily go that direction, though, for the primary. Or out on the chain, the other chain. Okay. So in fact, the branches right by this higher branch point, weren't really the biggest ions here, though. But we don't see quite as much, so we see some small ones, like this is much smaller, or here. Loss of 15 would be 127, loss of the methyl. So, I don't know. That would also give a secondary, but I guess we're losing a smaller radical that way. All right. Okay, if we have some other functional group in it now, then the cleavage can be much more kind of selective. So this is our specific 2-ethoxybutane. Okay, so we have an ether. So in this case, the ionization is going to take place on the oxygen. So we're going to end up with a radical cation here. And then we can do either those alpha cleavages, or we can do the hetero nuclear cleavage. So let's draw these out. Let's see, how did I do them here? Okay, so if we first do alpha cleavages, I'm going to do these down here. So this could go down this way, and then it could cleave on either side. So this could break here. If it did that, I'll draw this one in green. We would get, what am I doing there? This plus this radical. And this ends up being, where do I have that drawn? I guess this is going to be an H here. This one is at 87. Pretty small. Okay, if we do the first electrons the same way, but we cleave this bond, right? So it's still just the alpha cleavage. It still would go here, but this way. So same thing, just on the other side. So this would give us this has H here, and this plus the methyl radical. Okay, what?
It's just methyl radicals. They're unfavored, and obviously because of the mass spec, but not because of the signal of the mass spec.
Right, but I think usually, if I think the stability of the radical is really only going to be important if the cations that we're looking at are relatively of equal energy. Mm-hmm. Because otherwise it's more the stability of the cation that's important rather than radical. Okay, so this one would form ion 73. So that's here. Oops, not 9. 73. Okay, so that one's bigger, actually, than the one at 87.
Wait, is that?
Hmm?
So the M to Z is...
Oh, those are those backwards? 87, 73, yeah, because we lost a bigger group. Let me, where am I in here? The ethyl group? Oh, yeah, this one is 87. This is 87. Oh, that's way up there. Shoot. This one is 73. 73. Okay, so this here's 87. 87. Oops. Let me do them in the right colors. 80. Ah! 87 and 73 was in green. 73. All right, we can also do another alpha cleavage from this, which would go the other way, up here. Okay, but this would also form 87, right? Because the double bond would be up here. Plus methyl radical. So this should also be 87. 87. Okay. So, it turns out that the 87 and 73 down here can also do another rearrangement. So there's a rearrangement that looks like this. So if it has a hydrogen on here, then the way that this is drawn is that this hydrogen transfers over here and it loses an ethene. And so that would give us an H here, and a plus like this. And this one is at 45. So that, in fact, is the base peak. This one over here could do the same thing because it has this ethyl group on the oxygen. This can transfer over there, and this loses that ethene. Plus this double bond, and this should be 43, so this should be 57. Let's see, that one, 73. 45, 87 goes to 59. 59. Okay, so the other thing that can happen here, so these are all essentially starting with this alpha cleavage, but then two of them have another rearrangement afterwards. The other mechanism is the heterolytic cleavage mechanism, which would be something like this, where we have a plus here, and that involves the cleavage of the bond adjacent to the oxygen like this. Okay, so if we do that, that just gives us this carbocation plus the oxygen radical. And so this one would be at 57. Okay, so we have a couple that, well, there's 50, here's 57 down here. 29. We could also do the same thing if we did it up here. And it cleaved on this side. Then that would give us 29 plus oxygen. So 29, here's 29 here. So with a little work, and I had to look some of these up, because the rearrangements weren't something that I was so familiar with, we can account for a lot of the big ions in here. But I think the important ones usually are the alpha cleavage, which is the first step that we did at the beginning, and then this hetero cleavage. Those are the ones that I would usually, these two and these first steps over here are usually the ones that I would look at. But we do have both the oxygen and both the cation and the radical that can trigger rearrangements. All right, so this is another ether, but it's a ditert-butyl like this. So we could make the cation here, or the radical cation, and then this could do alpha cleavage. So remember, that's pushing this electron, and we'd lose a methyl group. Okay, so if I go over here, then we're going to end up with this plus a methyl radical. Oh, so one thing we got to figure out here. Okay, so this one's very branched. So ditert-butyl, what do we have? 4, 8. So this is C8H18O, which has a mass of M over Z equals 130. Right, so notice there is no 130. Okay, so because there's so much branching here, it cleaves more readily, and we do not see a molecular ion. And so the first ion that we see, notice, is at 115, right? So if we didn't know that this was a fragment ion, we'd get really thrown off, right? Because we'd say, oh, if this is the molecular ion, it's 115, we must have nitrogen in it, right? But in this case, this is a fragment ion because we're losing, right, from 130 to 115, we've lost a methyl group. Oops, 115. Let's make that better. Okay. Let's see. The other things we can do here, I'll do this here. If we just do the hetero cleavage, then this would give us this radical plus the tert-butyl cation, right? And that has a M over Z equals 57. Okay, so that's the base peak. All right, but we also see this prominent peak at 59. And so I think that ends up getting generated by a rearrangement like we saw on the last one, right? So this can go over here, and this can go here. And we just end up with a hydrogen here plus this neutral alkene. And this has a mass to charge of 59. Okay, so that's 59. All right, so both of the ethers we've seen, as long as the ether, if it has something like this, then, and it cleaves on the other side, right, then it can do this second rearrangement. Right, because we see this. We see this going over here and this closing here. Okay. All right, so halogens. Right, so we've seen them. Now we see the molecular ion is up here. 164 and 166, right? Because we have the M plus and the M plus 2. Here we have 135 and 137. So we know that this ion still includes the bromine, right? So we've lost whatever, 164 to 135. 164 minus, what is that?
It's 29.
Minus 29. So we've essentially lost an ethyl group somehow. When we get down to 85, then we could do 164 minus 85 equals 79, right? So that's loss of bromine, 164 to 85 minus 79. But if we go from 166 to 85, 166 minus 85 is 81, right? So we've lost. We have one molecular ion that has bromine 79. We lose that, we get 85. One bromine has isotope bromine 81, and we lose 81, we get 85, right? So we get the same one after we've lost the bromine, right? But we have the two different isotopes that we start with. Okay? We essentially have two different molecules, right? Because the two different isotopes. In one case, we have 79. We lose the 79, we get the ion that doesn't have bromine. And if we start with bromine 81, then once we lose that, we get to the same point again. Okay? So, if we ionize on the bromine, okay, we can do just this heteronuclear cleavage here. And if we do that, we just end up with this cation plus the bromine radical, right? And so this would give 85. We can get some of these other smaller ones from here too. We can do another cleavage like this. And if we do that, that gives us this plus this. And so this is 28 lower, so this is 57, which is, I guess, here. You can also get things that take place apparently like this. And if we did that, we would get this cation, but you end up with a cyclopropane. And this is 43, which is the base peak. And I don't know if we can make that any other way. Now the loss of, well, here, loss of 29, we have bromine still in the molecule. So what, let's see here, 135, the red one. Okay, so we can get some kind of, if I have room down here, maybe I can move this whole thing. Oops, move that up a little. I'm going to draw this like this. And we're going to make the radical cation here. So we can also get some things like this, apparently. This bond closes up here, and we have a cyclization like this. So this would create a 5-membered cation plus, we lost 29. So this would be 135 and 137. So it forms this 5-membered ring. 107. Notice there's 107 and 109 in there. That's a small ion that has bromine in it still as well. And that one apparently does a similar mechanism here, but this combines with this bond. So it makes this bromonium ion plus this radical, and this would be the 107 and 109. So, I think that a big loss is just the loss. An important one, of course, is just the loss of the bromine, right? And it's important that we can see which ions in here have bromine and which don't, okay? And for a lot of our stuff, just seeing that there's bromine there is going to be a big deal. So where were All right. This one has chlorine. I think we might have looked at this one before. Just when we were looking at the presence of chlorine, right? So this has this 3-to-1 ratio between 156 and 158. All right, and essentially none of the others have any chlorine in them. Okay, so here I'm just going to draw the structure and then we'll do the cleavage. So this is an ether, but it has chlorine out here. Okay, so looking at the spectrum, what else can you pick out just looking at the spectrum?
77.
77, right? So somehow it's going to cleave to here, right? So basically it's going to ionize here, and this is going to cleave like this, all right? And so this generates 77.
Plus 17, so that's an alcohol. So, well, it's a oxygen with a hydrogen on it. The 94.
94?
Yeah. So plus
Well, what else is important about that 94?
Base peak?
It is the base peak.
Other than
Notice that it's the only fragment ion that has an even mass.
oh, yeah, that is yeah.
So what does that tell us?
There's a rearrangement.
There has to be a rearrangement, right? Because this is an odd electron ion. This is an even electron ion. No, it's not. It's another odd electron ion. Even mass means that there has to be a rearrangement. Okay, so we should be looking through here and we go, oh, aha, right? It's got an even mass fragment ion, starting with an even mass molecular ion, and so it means there has to be a rearrangement. So, of the rearrangements we've learned so far, what do you think might fit for this one?
Like Andrew was saying, the oxygen is going to steal a proton from somewhere.
Right, the oxygen needs not so much a proton, but a hydrogen atom. Right, so we have to transfer a hydrogen at least over onto that side. It doesn't necessarily need to be on the oxygen, right? But we need a rearrangement here. And the way that I would do this is to draw this like it's ionized, in this case, on the benzene ring, right? And we can do this kind of, McLafferty type of rearrangement that we showed doing with the benzene ring. Right, so we can transfer one of these hydrogen atoms over onto the benzene ring, right? This has a hydrogen on it already. So we have two hydrogens here. Cl. We have a plus over here, and the radical is now over there. So then we do this alpha cleavage from here. This goes there, this goes there, and this goes up there. So this is an oxygen radical. This has two H's here, a plus, like that. And we've lost this alkene that has the chlorine attached. Okay, so this is like, we go back and we look at those rearrangements. Okay, and so this has M over Z equals 94. If we use the oxygen and we do an alpha cleavage from here, which is one of our main mechanisms, that goes to, we'd have this double bond here with a plus, and we would be losing this radical. This has M over Z equals 107. Okay, so we just used all three, basically everything except for a sigma cleavage, we used all three. We used the this alpha cleavage is the first one we looked at. It's the homolytic cleavage to go to here. We did the heterolytic cleavage. We cleaved this to here to get to 77. And we did the rearrangement that was, you know, kind of the McLafferty type rearrangement to get to 94. Okay? We used all of them here. All right, so alcohols. 1-hexanol, which has, C6H14O should have a molecular ion at 116. So we don't, well, unless, I don't know if you can see it, I think there's a teeny tiny little red dot down there, but it should be out here. So there's another case where we look and we see all these fragment ions all have odd, or all these ions have odd masses. So, you know, it either means that we have a molecule that has nitrogen in it, or we're not seeing the molecular ion. Okay? So this is 3-methyl-3-hexanol. 3-methyl-3-hexanol. Okay, so this can do these alpha cleavages, right? We're going to ionize here, and these electrons can be pushed down into here, and we can cleave any of these three bonds that are alpha, right? So we should be able to lose the methyl group, right? Minus methyl. So that should go from 116 to 101 minus CH3. We could lose the ethyl group, same mechanism. So this would be loss of ethyl. And so this gives us 87. Or it could lose the propyl group, right, on the other side. Cleave it here. So here, minus CH2, CH2, CH3. This would give us this, which is at 73. Minus 73. All right, so it's all these alpha cleavages. All right, let's see. Oh, that's another ether.
Do we care that much about the smaller ions, or do we care?
You mean
more
all
about-
this stuff down here?
Yeah, because like
Yeah.
18, that's you lost a water there.
Yeah, but that would have to be like a water cation.
Yes. Which
No, we don't really care about that down there.
Okay, understood.
Because once you get down so low, I think it doesn't really give you very much structural information if you're just seeing an ion of a very small piece. Like, oh, here's 29. You're like, oh, maybe we've got an ethyl cation. Or here's 15. Right? Those don't tell us very much because, so many molecules would have that. But I guess all of these other things below, have to be generated. I don't think that they're going to actually, just do sigma cleavages out here.
Mm-hmm.
So, it may be that they go to here and then they cleave again or something.
So it's similar to like IR.
Yes. And that, we want to, especially be able to figure out these higher mass peaks. This is kind of the functional group range, is the stuff that has logical losses that we can, figure out.
Okay. So I have a question.
Yes.
On the previous one, do you?
All right. So this one kind of shows everything already. So it would, ionize here. Then this would be an alpha cleavage. This would be an alpha cleavage. And then these are the two, I don't know what I think he called that an I cleavage or something, but these are the heterolytic, where the electrons just go like this. Same here. So we have those two main cleavages here. And we see, right, 115, right, is here. And I guess we do see the molecular ion, 130. We have 73, 71, 43. All of those are shown on there, right? So those are kind of following the standard mechanisms. Okay. Dang, I got a million of these things. Which one is this? Oh, that's not even in here. Now let's skip that one. Okay, what about an amine? Look at this one. It's got, I don't know how many carbons it has there. A lot of them. 185 molecular ion, odd mass, right? And basically we see one main ion at 30, right? And this is just going to be an alpha cleavage from this nitrogen, like this. It's going to give us this ion plus this radical, and this is M over Z equals 30. So any like long, primary amines like this that have some chain off of them are going to give this same predominant ion. It doesn't give us much else. And we don't see much of this, right? If we have this plus, we don't see this cleavage, this heterolytic. Okay, we don't see that for amines very much. Nitrogen is much better at donating the electron to give this positive charge. All right, so ketones can do alpha cleavages as well. So they're going to ionize on the oxygen, and the alpha cleavage we draw like this. This goes down here. This goes here. And this goes over here. So if we did those, we would end up, we could draw it like this. What?
It's just triple bonded to.
Well, this could be in resonance. We could also draw it resonance like this, where we have the plus charge here. So this is essentially an acylium ion. So we could do it there. That gives us 43 as our base peak. We could do it to the other side. We'd lose methyl, but we don't really see that here. From 128, it would be like one of those teeny ones. So we don't see much of that. What about this ion here?
Oh, it's an alpha cleavage, right? No, yeah.
Well, we're going from, you can't hardly see this, 128 to 58.
Oh, it's a rearrangement.
Right,
Yeah.
right? Even mass. It's another odd electron ion. Right, so this is going to be the classic McLafferty rearrangement. Right, so we have it like this. What's this? CH2, 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 CH, like this. All right, so it ionizes over here. I'll just do this all in one step. We can transfer the hydrogen atom. This can go down here. This can go to here. And we end up with this plus this. This is M over Z equals 58. Right, so it's an odd electron ion because we transferred the hydrogen over there. And because it has a radical and a cation on it.
So then the name of the game is basically trying to find as many 1.5 HATs as possible. Because that's what that's,
A lot of the rearrangements.
yeah. I mean, it makes sense, but
Mhm.
that's,
Right, because this goes through a 6-membered transition state here, right?
yeah.
Well, I think it's kind of the other way around too, is we're looking at our spectrum and we should recognize that this is an odd electron ion.
Mhm.
And that means that we have to have a rearrangement.
Okay.
And if we have a ketone or an ester or any of these carbonyls, then this is the likely one, right? Or the aromatic ring like that. The main thing is we just have to have this system where we have the pi bond and we have alpha, beta, gamma. We have to have a proton at that position for this type of rearrangement. Oh, we're out of time. So let's stop there. The next ones kind of gives us some choices, and we start kind of solving some things. So yeah, I don't think we're always going to be able to, rationalize so many things. And some of these rearrangements that I did with those ethers, well, now that we've done them enough, maybe we can look for them. But, other than when we're just specifically doing mass spec now, if we mix it in with NMR and all those things, likely that much of our information will come from NMR, and then we'll use mass spec and IR to supplement.